All right, we're about to go on a journey back to the very first moment of the universe, to take a look at a substance that existed for just a microsecond, but ended up creating everything we see today. We're talking about the universe's primordial soup.
So what is this stuff, really? Well, what if I told you that scientists have actually created a substance that holds a bunch of cosmic records all at once? It's hotter, denser, and flows more perfectly than anything else we've ever seen. Let's break down just how wild those records are.
And when I say records, I mean extreme. This is the hottest matter ever made in a lab. We're talking over 250,000 times hotter than the core of our sun. It's also the densest stuff we've ever created, packing matter up to 50 times tighter than in an atomic nucleus. And maybe the weirdest one? It's the most perfect liquid, which means it flows with almost zero friction. Oh, and one more thing. It was the very first liquid to ever exist. So what on earth is it?
To really put that hottest ever claim into perspective, look at this number. That's the temperature we're talking about. Not thousands, not millions or billions, 1.8 trillion Kelvin. That was the temperature of our universe in its very first moments, when this mysterious substance was the only thing around.
To figure this out, we have to rewind the clock. A lot. We're jumping back 13.8 billion years, right into the very first moments, after the Big Bang.
So in the absolute first fractions of a second, the universe was expanding and cooling, and the fundamental forces of nature were just starting to peel apart from each other. And right in this incredibly brief window, about 1/1,000,000th of a second after the Big Bang, before protons and neutrons could even think about forming, the entire cosmos was filled with this primordial soup of totally free-roaming, fundamental particles.
And that brilliant, chaotic soup, it has a name: Quark-Gluon Plasma. You'll see it called QGP. This is the answer to our mystery. It's this incredible state where the building blocks of all matter, the quarks and the gluons that glue them together, aren't locked up inside protons and neutrons like they are today. Nope, they're totally free.
So what is this plasma actually made of, and what kind of rules does it play by? Let's dive into the physics of this amazing cosmic glue.
The recipe is actually pretty simple. You've got quarks, which are the fundamental particles that build the protons and neutrons inside every single atom you see. And then you have gluons, which are, well, they're literally the glue. They are the particles that carry the strong nuclear force, binding those quarks together.
Now here's where it gets really weird. The strong force has this paradoxical nature. At normal energies, like in our universe today, the force gets stronger the farther apart you try to pull two quarks. It's like an unbreakable cosmic rubber band. That's called color confinement. But at the insane energies of the early universe, the exact opposite happens. The force gets weaker, and the quarks can just drift around freely. That's called asymptotic freedom, and it's the absolute key to unlocking Quark-Gluon Plasma. Okay, so if QGP only existed for a split second right at the beginning of time, how in the world do we study it today? Well, turns out we figured out how to forge this primordial soup right here on Earth. And the answer is, we make our own miniature Big Bangs. Seriously. Inside massive particle accelerators, like the Relativistic Heavy Ion Collider, or RHIC, and the Large Hadron Collider, or LHC, scientists do something incredible. They basically melt protons and neutrons by smashing heavy atoms, like gold or lead, into each other at nearly the speed of light.
The whole process is basically a Big Bang in a bottle. First, you get these heavy ions going at 99.99% the speed of light. Then, bam! They smash together, creating a tiny fireball of unimaginable energy. For just a fleeting moment, the protons and neutrons inside literally melt, releasing their quarks and gluons and forming a tiny droplet of QGP. This whole fireball then expands and cools in just 10 to the minus 23 seconds. I mean, that's a time scale that's almost impossible to even imagine. Scientists then have to analyze the thousands of particles that spray out to figure out what that QGP was actually like.
So this is the crucial question. After all that work, when they finally created this plasma, what did they find? What were its properties?
Well, it turns out nature had a pretty spectacular surprise waiting for us. You see, physicists had a clear prediction. They thought they'd find something like a gas, with quarks and gluons just zipping around freely, not really interacting with each other. But that is not at all what they found. Instead of a gas, they discovered that Quark-Gluon Plasma behaved like a strongly coupled, nearly perfect, flowing liquid. I mean, this discovery completely shattered expectations.
A substance made of fundamental particles at trillions of degrees was acting like a drop of water, but with practically zero friction. It was a total game changer.
So how did they figure this out? Well, one of the key pieces of evidence is something called jet quenching. Sometimes in these collisions, you create back-to-back jets of high-energy particles. Normally, they just fly apart with the same amount of energy. But if one of those jets has to travel through the droplet of QGP, it gets massively slowed down, or quenched. Sometimes it gets completely absorbed. That's a huge clue that the QGP is an incredibly dense liquid, not some thin gas.
And this right here is a brilliant way to visualize it. In a really recent groundbreaking discovery, scientists found direct evidence of quark wakes. Just like a boat creates a wake when it moves through water, they saw fast-moving quarks creating these tiny ripples in the QGP right behind them. This is basically the smoking gun that proves its liquid nature. It's incredible.
Okay, so why does any of this matter? Why spend all this time, money, and energy studying a substance that vanished from the universe 13.8 billion years ago?
Well, because studying QGP is about unlocking the most fundamental secrets of the universe. It's about understanding our own origins, how the protons and neutrons that make you, me, and everything we see first formed. It lets us test the rules of the strong force, which is the most powerful and, honestly, the most mysterious force in nature. And get this, it might even help us solve other cosmic mysteries, like figuring out what's going on inside the superdense cores of neutron stars, where QGP might actually still exist today.
And this quest is far from over. The RHIC Collider at Brookhaven National Lab is actually being transformed into a brand new machine, the Electron-Ion Collider, or EIC. This next-generation experiment is going to use electrons to create what's essentially a 3D map of the inside of a proton, giving us this unprecedented look at the glue that holds all of us together.
Which really just leaves us with this final thought. The discovery that the primordial soup of our universe was a perfect liquid, not a gas, was a complete and total surprise. It's just a powerful reminder that every time we look at the universe in a new way, we find things we never, ever expected. So the real question is, what other secrets are still hiding in those first few moments of existence, just waiting for us to find them?